Greetings and welcome to a new video about analog electronics. We continue with our BJT circuits and this is our example number 4. In this example I would like to continue on the discussion of bias stable design, and in this case we'll look at the 4-resistor biasing instead of 2-resistor, because in example number 2 we saw the configuration with 2 resistors and also 2 DC voltage sources. And this is the effect of the beta, which is the current gain of the BJT component. Of course, we will work out everything in the calculation step by step and also verify those in the SPICE simulations. So let's look at our circuit. We have this circuit given. We see one DC voltage source, VCC, which is 15 volts here. And we also have the VBE, which is the transistor base emitter conduction voltage. So this is the 0.7 volts. And we have now 4 resistors, R1, R2, RC, and RE. So the values are shown here. What we would like to calculate is the IB, the base current, the collector current, and the emitter current, and also the VCE, which is this voltage, for the condition when the beta is 100. Now in question B, we repeat A, but then changing beta to 200, and in question C, we make it 300. So we see now 3 conditions for beta, and that will be then done for these 4 unknowns. So let's look at the solutions. How can we work this out? We can use in this configuration, and we should actually use in this configuration, the Thevenin equivalent circuit at node B, which is then shown here. So what is a Thevenin equivalent circuit? We have discussed this in a playlist about electric circuits and specifically considering Thevenin's equivalent circuit, also Norton equivalent circuit. But let's review this. We will actually transform this circuit in this configuration. So we see the B is still there, which is the node. The base current is there, and we would like to now connect in this configuration a resistor, which is called the Thevenin resistance, and also the Thevenin voltage, which is then this series combination. Now we can set up here the equation which will give us the exact value for the base current and the other parameters. Now how do we calculate the RTH and the VTH? So how do we calculate the Thevenin resistance and also the Thevenin voltage? First with that one, that is actually calculated in this format. You look at point B, the node B, and then disable the voltage source, VCC, the DC voltage source, and you look at what kind of a resistor you see. That's the parallel combination of R1 and R2. So you look actually back from the base node. So R1 and R2 in parallel means this formula. And if I now substitute the values for dk times the 10k over the summation of these 2 resistors, you will get 8 kilo ohms. Okay, that's for the Thevenin resistance. Thevenin voltage is the voltage at this node when you make voltage division. In this case it is the VTH is R2 over R1 plus R2 times VCC. Now if I now substitute the values here, you will get 3 volts for the Thevenin voltage. Now we have everything in this equivalent circuit configuration. This is 3 volts and this is now 800 of 8000 ohms or 8 kilo ohms. Okay, at the input load in this part of the circuit, beginning at this node all the way getting back to ground, and that equation is then given by this VTH, the Thevenin voltage, is equal to Thevenin resistance times the IB, this voltage drop using Ohm's law, plus the VBE, and plus the voltage drop across RE. That's all shown here. Now we have now 2 unknowns here, which is the base current and the emitter current. Now let's now make for this equation just one unknown, and we can now use, assuming linear region of operation for the transistor, that the emitter current is beta plus 1 times the base current. Now if I combine now this or substitute the base emitter current expression in here so that we get only the base current, then we have the following expression. And you can now see that the IB, which is the base current, is the only unknown here. Because we know everything for this equation except IB. I can now collect the IB terms also, so make a large coefficient in front of the IB. Now if I now substitute the values and also rewrite this in terms of IB, I have this expression. This is now the expression for the base current. Now for specific condition, the beta is 100, I can calculate now the IB using this expression. Now what do you see? you see 3 minus 0.7, which is this part, numerator, and then 8000 for the RTH, so the Thevenin resistance, plus 800 times 101. And it will give you approximately 26 micro or 25.9 microamps for the base current. Now, assuming of course the linear region of operation for the transistor, we can say the collector current is then the beta times the base current. We have the base current, that will be then 100 times this 25.9 micro, and you will get 2.59 milliamps. In a similar case, we can calculate now the emitter current, which is shown here. Again, the same format. 101 times that base current, you will get 2.62 milliamps. So we have now the currents for the condition where the beta is 100. In order to calculate the VCE, we look at the output node here, which is the Kirchhoff's current law for this case. So we say Kirchhoff's current law at the output loop, and we can now set up the equation there. It's just VCC is equal to this voltage plus the voltage here plus the voltage there. Now, in order to get the VCE, I need to say VCC minus the two voltage sources here, or voltage drops there, and we have now this expression. We know IC, we know IE, we also know the values here for the VCC and the resistors. If I now substitute that, you will get 7.73 volts. Now, we will now repeat the process for the question B and C when the beta is 200 and 300. So this is just a repetition for these calculations. Okay, let's now move to the beta is 200. Again, the same expression, but just beta here 200. Now you will get 13.6 microamps for IB. And if I now do again, IC is equal to beta times IB, 200 times that base current, you will get 2.73 milliamps. And the emitter current, again, the same formula as we did in question A, you will get 2.74 milliamps. Okay, now, again, using the Kirchhoff's current law in this output loop, we can set up this equation again and then rewrite this such that we get the VCE. And if I now substitute everything, the new values for the collector current and also the emitter current, you will get 7.36 volts. That's for the situation B. Now, going to question C, but the beta is now 300. Again, the same equation, but just beta is changed. Everything is exact same as before. So we get this, and now it will be 9.24 microamps. Again, using the formula for IC, they will give me now 2.77 milliamps, and for the IB, I will have 2.78 milliamps. Again, the same expression here for the collector current, collector emitter voltage, I mean. So we will get then 7.23 volts. So we have now for A and B and C, for three conditions of the beta, the required four values here. Okay, let's make a summary of the results. It's always handy what we have just calculated. This is the question A, B, and C, and these are the betas 100, 200, 300, and this is the base current, collector current, emitter current, and the collector emitter voltage for each case. You can see the following here. The effect of variation in beta will cause the base current to change. So it is changed and dramatically. But the collector current and emitter current and also the collector emitter voltage are not that much change. It is, okay, a little bit change, but it is quite stable. So that's why we call it bistable design. And this feedback resistor, it's called the feedback resistor of RE, will cause that stability. If this is changing, so you make it a little bit larger, you will get more stability. If you make it a little bit smaller, the stability goes down. It depends, of course, also on other resistor values in your circuit. But now this is the conclusion, what you see here. The beta will go up from 100 to 200, so that means 100%. But the collector current is not that much change, and also the collector emitter voltage. And those two, the collector emitter voltage and the collector current, are very important for the biasing of your transistor circuit. Now, the DC load line equation is also very important. That's given by the output loop. which is then the VCE expressed in the parameters here in the output loop. That is shown here, just using Kirchhoff's voltage law. Again, we need to set up an equation where we have only IC and a VCE. Now we can then use IE equation to emitter current in this format. And the collector current is given by this, using the base current. If I now rewrite this collector current again, so IB is equal to IC over beta, and then substitute that in the expression of the emitter current, I will have this. And now I can substitute this expression in here, such that we get only IC in the expression. Now we get this, and this is then the equation we can use, and this is the load line equation for this circuit. You can see the coefficient actually in front of the IC, and this is the starting of this line, which is then the VCC. And this is a decreasing line, it's a linear line which will decrease, which has a negative slope. Okay, let's see. We have now a couple of situations. Beta is 100, it will change of course. Beta is 100. If that is given, that will be then 15 minus, now you get here RC, which is 2000 plus 800 times 101 over 100. And that is this value. But since this 100 over 100, and also for the situation for beta is 200 over 201 over 200, and also for the beta 300 is 301 over 300, is very close to 1. So you can see the results here. So this is the expression for the load line when the beta is 100. This is for the beta is 200, so you can see this very small change in this coefficient. And for beta at 300, you only get this. So you can see this is not that different from each other. And you can now consider this actually just as one load line, DC load line. It is actually in effect 3 different load lines, and the endpoint is here, but they have a different slope. But still we can assume that they are exactly equal to each other for our discussion. So the error will be very small. Okay. The VCE is, by the way, between 0 and the VCC. That is the limit, those two. And we also have an IC which starts at 0, goes to the maximum value here. That is given or found from the load line equation. Okay, let's collect them. These are the results for the DC load line equations. And this is the plot we can now make. This is now the collector current and the y-axis, and the horizontal axis I have the VCE, which is the collector-emitter voltage. Now we can say this DC load line equation starts here and goes down all the way to 15 volts when the current goes to 0. Now, how much is this? This is really determined by this expression, which is the maximum of the IC, which is IC max. And now if I now substitute the value for the VCC and also the beta plus 1 over beta and also the resistors, this is then 5.34 or 5.35 depending on the beta, but it's very close to that value. Now we also have now these two values, so we can draw this pink line, and this is our DC load line. Now we have now 3 conditions. Beta is 100, 200, 300. Let's see what we have. The first case for beta is 100, these blue dots. This is then 7.73, which is then the VCE, and that will correspond to 2.59 milliamps. Now that's then the point A. The red dot with these dashed lines will give me 7.36 volts and the corresponding of 2.73 milliamps. And that is the point B. And for the green part, it is the final one for beta at 300. You can see that this green dot is now appearing there with these dashed lines for the X and Y values. You will get 7.23 volts for the VCE, and the collector current is 2.77 milliamps, which is shown here, and that's then this one. What you see here is these 3 points are very close to each other. It's not really that much change. When you change the beta dramatically, that is actually the message here. So we can say this is kind of a very stable biasing design. And it is also seen here in the change, the percentage change from going from beta as 100 to all the way to 200, so 100% up. The base current will go approximately 90% up or down, depending on, of course, how you look at it, but there's this change of 90%. But the collector current goes only approximately 5.2%, not that much. And emitter approximately 4.7, and the VCE approximately 5%. So on average, just 5% change in our important parameters, while the beta goes from 100 to 200, which is then 100% change. Now looking at the same situation, but then for the beta is changing from 100 to 300. That is 200% change. You see the IB is changing dramatically, but the IC, IE, and the VCE are changing approximately by 7%. So this one is 7.1, 6.4 for the emitter current, and also here 6.9 approximately. So approximately 7%. Still really nice, and that's why it's called a bias stable design, because this dramatic change from 100 to 300 is not really happening all the time. This is just to make it look like very drastically happening. But this is really nice to see. If I make my beta very, very large compared to the actually assumed value, still we have a very small error, just 7% in our current and also in the voltage. Let's see how we can see this also in the simulations. Now this is the simulation circuit here. We have now the NPN BJT, the transistor here. This is the base current, the collector current, emitter, and the collector-emitter voltage. You see here 26.2 microamps. We have 25.9 microamps, so small error. In the collector is 2.63 milliamps approximately. We have 2.59 milliamps, also very small error. In an emitter, we have 2.65 milliamps. We have here 2.62 milliamps. So you can see the error actually starting from the base current propagates to the collector and emitter voltage. And these are the values we have calculated, and these are the simulations here. For the collector emitter voltage here, VCE, it is 7.63 approximately volts, and we have 7.73 volts. So approximately 100 millivolts error in the collector emitter voltage. Now this is for beta is 100. Now going to beta is 200, exact same circuit, but just the beta has changed now from 100 to 200. You can see the base current is 30.8 approximately. That's very close to what we have calculated, 30.6. The collector current, also very close to what we have, 2.76 milliamps for the simulation, and we have 2.73 milliamps. And the emitter current is 2.77 milliamps, we have 2.74 milliamps, also very close to what we have calculated. And the collector emitter voltage is 7.26 volts, and we have 7.36 volts. Again, 10 millivolts larger actually than the simulated value. So kind of a static error we have here. Now looking at the final one, which is then the beta is 100. So this circuit, you can see the base current, which is here simulated is 9.36 micro, and we have 9.24 micro. So our base current is always a little bit smaller. Then the collector and also the emitter current is also smaller than what we have actually here. So we have here 2.81 milliamps for the collector and 2.82 milliamps for the emitter current, and we have these values. So also a little bit smaller, and such that since this is our smaller, we have actually a little bit larger value for our VCE. That's 7.23 volts. We have now 7.13 volts. Again, 100 millivolts, kind of a static error in the collector emitter voltage. But those are still very nice results compared in the simulation and our hand calculations, just using very simple model for the NPN BJT transistor. Alright guys, this is our example, fourth example about the NPN BJT transistors having a 4-resistor biasing configuration here with just one DC voltage source. And this configuration will allow us to have a stable biasing while the beta is changing dramatically. You can also change other parameters like temperature or one of the parameters in the resistors, and you can see the effect there for yourself also. So try it out in the simulator, and it gives you a lot of insight in this circuit. If you have any questions, comments about this exercise, please let me know and I will try to answer them as soon as possible. We will continue, of course, with other examples, other topics, and I will post in the couple of days also about the PNP transistor example, also using the four-resistor biasing, and discuss the situation there. See you next time in another video. Take care.